Hi everyone, my name is Matthieu Vilain, and today I will be presenting my project, which is a Python library written in Rust to encode genomic sequences into numerical features. This project actually came from another project where I had to use some genomic sequences and pass them to machine learning models. And I realized there was no Python library that would conveniently regroup all the encoding technique used for genomic sequences. I also realized that genomic data sets are increasing in size, and it would be a good idea to have a package that would encode these sequences very fast. So with that in mind, I created a small Python library called dna-parser with the goals to be convenient to use, easy to integrate in other workflow, and also that would provide fast encoding for large data set, as I just said. The layout of the package would be to have a front end in Python, where we put all the functions to call the functions that are efficient. So the functions in Python would be some nice functions that are convenient and easy to use. And on top of that, using Python will make the package easy to install using pip. And then I also want to make sure that all the types that are returned to the Python side here would be NumPy, so it would be easy to integrate with other package like TensorFlow or PyTorch that can use NumPy types. For the encodings, because I want the encodings to be fast and Python is known to be not a really fast programming language, I decided to use Rust. In Rust, that's where all the functions for the encoding would be. And I picked Rust over C because it's as fast as C. It also allows for multi-threading, but it also guarantees memory safety through some rules that are enforced by the compiler at compile time. It checks your code and it makes sure your code is not going to create any memory problem. Pyo3 is also a plus in Rust. It's a well-documented package that links Python and Rust and that converts Python types into Rust types and vice versa. So with this, I started working on a first encoding, which is the one-hot encoding, where every nucleotide is represented by a vector of 4 possible values that take either 0 or 1 as a value. So A would be represented by the vector 1, 0, 0, 0, C by 0, 1, 0, 0, etc. Once I'd done that, I wanted to compare my implementation to other implementation. So what I did is I found two other packages, TensorFlow.io and SecPro, that also had a one-hot encoding. I then took a benchmark dataset on GitHub that has 154,000 sequences available that were around 250 nucleotide long, and then I repeated the encodings 10 times for each library. Here the times are log transformed, and dna-parser performed fairly well, with the encoding time decreasing as we used more cores. Compare, for example, to TensorFlow.io that was surprisingly slow, taking over 5 minutes, I think, to encode the whole thing. But dna-parser was not as fast as, for example, SecPro, that automatically used all the cores in your machine, and that was slightly faster. As a second encoding, I also wanted to implement a term frequency inverse document frequency, which is an encoding that is usually used in natural language processing, where the idea is that if you have different multiple sentences, you can represent each sentences by the frequency of the words that compose it, compared to how rare each word is across all the sentences. So here, for my implementation, I compared it to the implementation in the scikit-learn package, because TensorFlow.io and SecPro did not have any term frequency, inverse document frequency implementation. For first implementation, we can see that it scales, so the complexity is the same that scikit-learn, which is a good news, but unfortunately, dna-parser was much slower than scikit-learn. Here, the times are also log transform. So dna-parser took around 27 seconds to encode everything, while scikit-learn took probably around 1.5 seconds. Additionally, I have two extra encodings, which are the cross encoding and the ordinal encoding, that are implemented similarly to the one-hot encoding. And those encoding are already pretty efficient, but could be faster, for example, by returning a single numpy array instead of a list of numpy arrays. And that would also make other things in my implementation a bit simpler, I think. The first implementation of the TF-IDF encoding, as I just say, worked, but is also slow compared to scikit-learn, which is why, as the next steps in the project, I would like to re-implement the TF-IDF and also try to parallelize part of it, which I believe hasn't been done by scikit yet. Other ideas also include implementing a way to load sequences in batches if the whole data set does not fit into memory, and then adding a folder with some tests. So while this library is still a work in progress, I believe that it shows that combining Python and Rust shows promising results to process a large data set of biological sequences, and that it also shows that it can be a powerful combination to create tools in bioinformatics. You can find all the codes on my GitHub, and thank you very much for listening, and I hope to see you at the conference.